So hi everyone, I'm William from TikTok, and originally we have another colleague that would talk about this slide with me, but he won't be here today, so I will be the only one who is presenting it. So it's gonna be a Nightling talk again. So I will talk about Bytebricks, and it's a generic high-performance VPN framework that we work on at TikTok this year. So for this presentation, I'm gonna start with background and goals, and then application design in the beginning. And then after that, I will get into more details, for example, the implementation challenges, how we implement the framework. And then at the end, I will close the presentation by talking more about the performance result and the future work. So for the background and goals, we wanted to design a VPN application that can support multiple different protocols at the same time. However, if we were doing it in the traditional way, using scalar processing, it doesn't seem to be a suitable choice due to its complex pipeline, the difficulties to decouple control plane and data plane, as well as the feasibilities in terms of extending the application. We then thought of using the DPDK graph library to design such application, as it seems to be to do a better job. Some benefits that you can think of, which include but not limited to, for example, the ability to accumulate packets, reduce iCache misses, and also to have more manageable and better code reusability depends on your business requirement. So for the application design, we use, as I just mentioned, we use DPDK graph library and also the DPDK crypto dev library, which you can see on the right-hand side. Apart from the RX and TX node, on top level we have pre-processing nodes, and then after that we have some VPN nodes that will correspond to some VPN protocols. As well as, and then after that, we will have a post-processing node. So for pre-processing nodes, it obviously includes some nodes, for example, nodes for packet classification and IP lookup, or even a node for example, an ACL node if the user wish to implement this kind of logic. And for processing node, it's kind of similar to pre-processing node. Pre-processing node, as you can imagine, you can probably also define some logic, for example, IP tunneling and ACL as well. So before moving on to the details from our implementation, we just want to highlight that currently we have only implemented the Wireguard protocol for our application. The reason is that Wireguard is more lightweight and less complicated than the other protocols, for example, the IPsec. And at the same time, it is also a popular choice in developing any VPN application in the industry. So now let's quickly go through what the typical workflow from the Wireguard protocol would look like. So as you can see, I have labeled the left side as the initiator and then the right side as the responder. So what can happen? I guess it's pretty much self-explanatory, but I will just quickly go through it. So what happened is that the initiator will send a handshake initialization packet to the responder, and then the responder will send back a handshake response to the initiator. And then if all things go well, the connection is established successfully, right? And then after that, the initiator and responder can start to transmit packets back and forth. But some special case can also happen as well. As you can see, I have labeled the blue color in keep alive packets and handshake packets, handshake initialize packet after 3 transport data packets. Well, I believe that keep alive, this name is not uncommon to everyone here. So what can happen is that, let's say the initiator sends a packet to the responder, but the responder doesn't actually have anything to reply to. So what happens is that the responder will have a trigger on, so we will have a timer on its side, and after some certain time period, it will send a keep alive packet to the initiator to tell the initiator that, oh, this connection still exists, but I just don't have anything to reply to. Well, other case can also happen as well. As you can see, in the bottom 2 packets, the initiator sends a transport data packet, but somehow the responder is not sending anything back, so including the keep alive packets. So in this situation, the initiator will think that there must be something wrong with the connection. So there will also be a timer to be triggered to send a handshake initialization and trying to reestablish the connection. And on the right-hand side, it is the layout from the DPDK graph. And I will, and as you can see, it's actually not that complicated. You have a Wireguard input node, and then after you check the packet headers, and then if it belongs to the handshake packets, it would just go to the handshake path, and if it belongs to the data packets, it would just go to the data packets path. I will explain more about the how the timer works. As you can see, it's kind of get decoupled away from the Wireguard graph. So again, before digging into the details, for example, how we implemented the egress and ingress direction, we just want to highlight some of the implementation challenges that we kept in mind when we were developing the application, as they are more or less the most important parts to consider if we want to achieve high performance for our application. So the first three bullet points are more or less kind of overlapped, but after you read it through, you should have a better picture of what I want to deliver. So the first one is that packet processing from the same peer is not guaranteed to be in the same core regardless of the direction because of the RSS from NIC, right? And secondly, for optimal performance, packets from the same peer should be processed in a specific core only, because as you can probably imagine, which I've also written in the third point here, is that the egress and egress direction will interact with the timer at the same time. So it's kind of emphasize the second bullet point, that because we want to have the because the timer will interact will be interacted in for every packet in egress and egress direction. So obviously we want to have the best synchronization method to make sure that the timer operation is executed safely. So for the egress direction, and I also call it the encryption side because it's easier to be understood. So we use RT flow in the egress direction, and then with the flow rule matching the destination IP address. So in this mechanism, we can make sure that all the packets sending to a particular peer will be processed in one core. And also, different peers will be assigned to different cores, such that we can also have the benefit of load balancing. So this direction is pretty easy to be understood, but let's hold on for a second to rethink if we just solve the problems and challenges we just mentioned a couple slides ago. Well, is timer operation thread safe now? Well, if we just think about the egress direction, it pretty much is, right? Because we just use RT flow to kind of force all the packets to from a particular peer to be processed in a specific core. But the processing core of a peer can still be mismatched because we still haven't considered the other direction. So what's the potential solution? So the potential solution is that we can use log or to enqueue packets to a different targeting node. As I just mentioned, I forgot to mention bullet point 4, but yeah. So similar application from VPP uses intercore communication. So I call it ICC. Let's call it ICC. So what they do is that they would enqueue the packets to a different to the targeting core if the packets is reside in a wrong core. So these potential solutions use log definitely doesn't sound great. So and then obviously we want to do better than other existing solutions, right? So for the ingress direction and plus the timer, so what we did was that we used one extra core just for the timer operation, and then let's call it the assist core. So what the assist core will do is that other cores can enqueue the operation type, log the packet itself, regardless of the traffic direction. So as you can see on the graph that I drew, so each PMD or each core will keep enqueuing the different timer operations. For example, if the, for example, reset, start and stop operation are the most, probably should cover all of the timer operation that the user want to do. And then we also thought about using RT flow in this direction as well. But the problem is that not every NIC will support the raw item in RT flow, and then so we didn't do it in this way. But it's definitely a thing to try if you want to further optimize it for the whole application. So this is the performance test topology that we use. It's pretty simple as well. So we just have kind of like a symmetric setup. So we have two Bytebricks, one for encryption and one for decryption. And then packet generator will send the packets to the test PMD port where the decryption Bytebricks will be connected to. And we use Mellanox CX5 and also a Cascade processor from Intel. So for the performance result, first of all, we have been able to obtain some third-party library online which show performance from similar application, for example, VPP, and also there's one called Moonwire. So specifically, we will compare the performance difference between our application and VPP as they are the most comparable among all the candidates. And also to quickly mention that for the benchmarking hardware, VPP uses Intel Skylake processor while we use Cascade. So for a single core performance for 512 bytes, we outperform VPP by around 20%. And in terms of scalability, although we don't have data for VPP multi-core cases, we try to implement the ICC approach on our own. But what we saw was that the scalability was actually very poor for multi-core cases. So in conclusion, our results show that not only our application is able to achieve a higher performance in single core case, but it is also able to scale well. If you can see on the graph on the right hand side, if you were to increase the number of cores used, which you cannot see that for 8 cores. Well, technically it's one more core because we have the assist core for all of the timer operation, right? So for 9 cores, 1,500 bytes, we are able to achieve around 51 gigabits per second. And for the future work, we will definitely try to do more performance tests using hardware critical depth and also in production environments. And definitely worth to also try different VPN protocols as well. And last but not least, just want to quickly say thank you to other developers apart from Lorenzo and I. So Yue, Satish, and Lian. Yep. And that's all for the presentation. Yeah. Any questions are welcome if we still have enough time. Yep.
Yeah, thanks for the presentation. So do you see anything in the graph library where we need to improve from the infrastructure side?
Sorry.
Anything in the graph library where DPDK needs to improve?
That's a good question. I mean, most of the issues that we had when we were developing this application was more about how to decouple the control plane and the data plane. So for the DPDK graph, personally, I haven't thought of any yet. I think the only difficult part in using that library is the learning curve, because obviously comparing to scalar processing, you need to understand, what kind of logic you want to implement as a node, right? Yeah. But no, I haven't thought of anything particular. Yeah.